Alright friends, in this video I'd like to go ahead and take a first day for section 2.7 of your textbook, and specifically in this video we're going to begin our discussion of inverse functions. And so let's go ahead and get into that, right? So it says here in the box, suppose we have a function f of x is equal to 2x plus 3. So remember, we've talked about how functions are machines, and so this is the machine that would take your input, multiply it by 2 first, and then after that add a 3, okay? We can go ahead and visualize that a little bit more easily by taking a look at this flow chart right here, right? So our function f is going to take this input of x, which remember, it's always represent the input, and then it first multiplies it by 2, so of course the result for that is going to be 2 times x. And then after that, it's going to go ahead and add a 3 to that, right? So we're going to have that 2x that we initially had, and we're going to have the action of adding 3 to that result, okay? And then what we finally end up with here is going to be the output 2x plus 3. Okay, so remember that we coined these terms input and output, and I think this flowchart does a really good job of kind of describing what that function might do. Okay, now let's say that we wanted to go ahead and now undo what we just did. Okay, again, what we just did is we multiplied by 2 first and then added 3. If we're going to undo those two actions, then we better do the opposite of those actions and also in the reverse order, okay? So let's go ahead and start with the output that we had here, right? So that was our 2x plus 3, which is what we called initially the output, but now since it's what we're starting with in this new function, we'll go ahead and say that that's the input now. And so what's now going to happen is if we take that result and we subtract 3 away, that's going to be the expression 2x plus 3 that we started with. And now we're going to take that and we're going to subtract 3 away. Well, what's going to happen? Well, this plus 3 and this minus 3, those are going to undo each other and just simply leave us with the result 2x, okay? And now after that, we need to just go ahead and divide by 2. So we're going to have the 2x that we have, and we're going to divide that by 2. And of course, what's going to happen there is, you already know, 2 divided by 2 is going to make 1, and it's going to give us the initial x back that we started with, okay? But now since this is what we ended up with here in this new function, this is what we would consider to be the output of our new function here, right? So this first function process is something that we would call a simple function f. That's what we called it before when we said f of x. This new function down here, since it took in the expression 2x plus 3 and it gave us back the x, we need a new name for this. And since it's so very related to our initial function, we're going to name it f. But we're going to introduce some new notations so that this is what we call the inverse of f, okay? And you might have seen this before, but we use this notation of a superscript of -1. Now, that is not an exponent. That is just simply a superscript. That's just notation for us to recognize that this is the inverse function that we're dealing with here, okay? So whereas our initial function took in x's, f of x is equal to 2 times that input plus 3, our inverse function is going to take in inputs, and it's going to do what with them? Well, we just discovered here that that is going to simply take our input and subtract 3 first, because that's what we did right here. We subtracted 3 first, and then after that, we divided by 2 right here. Okay, and so our inverse function machine is going to look like that. It's going to look like take whatever you give it, subtract 3, and then divide everything by 2. These two machines are always going to undo each other. Okay, so if you feed an input into f and get the output from f, and then take that and then feed it into your inverse machine, you're going to get that original input that you first started with. Okay, and to maybe make that a little bit more concrete and clear, let's say that I had a machine that turns apples into bananas. Let's say that I call that machine f, right? So if I give the f machine an apple, it's going to turn it into a banana for me. But let's say that I'd like to take that banana and turn it back into the apple that I started with. Well, I would want to take that banana and I would want to go ahead and plug that into my inverse machine, and the inverse machine of f is supposed to undo what f did, and it's going to go ahead and give me my apple back that I initially started with. So that's the idea behind inverse functions, and what I'd like to do for the rest of the video is just go ahead and take a look at a couple of different function representations and dip that into the language of inverse functions here, okay? Now, what you may have noticed before is that I did stick with this language of input and output, and so what you may have noticed is that in the original problem, I had an input of x and an output of 2x plus 3. So that is the order of how my original machine goes, and the way we typically would write that with ordered pairs would be to say input as your x-coordinate and output as your y-coordinate. Well, if you go look at your inverse function machine, you'll notice that there's kind of a reverse action going there. What was the output is now going to become your input. So the x-coordinate down here in your inverse is going to be the y, and then we end up with the output over here as being the original input here. So basically, whenever you have an original function and its inverse, you have this swapping of the x and the y coordinates that occurs. So if I give you an example like here in number 1 where it says find the relation, we could do that simply by just going ahead and swapping the order coordinates that we given here. So we can make a new table. If this is the table that goes with the original function machine f, where I might say that right here, y is equal to f of x, then I can go ahead and create a new table for f of, sorry, not f of anything, but f inverse I meant, right? So we have our inputs and our outputs, and keep in mind how this works. We're just going to swap the coordinates that we find here. So if originally we had an input of -4 mapping to an output of 2, I'm going to swap those coordinates, and I'm going to say now the input for my inverse machine is a 2, and the output would simply be -4, okay? And it's the same thing going on through here, so I'll just go ahead and make that a quick process here, just kind of swapping those coordinates. 0, 0 would swap to 0, 0, and then we would have 1, 2, and then finally 2, 4. Okay, so just remember that when you're dealing with an original function and its inverse, you have this swapping of the coordinates that we need to kind of account for, okay? Now, one of the other things that I might ask you to do is like in example 2, where it's actually going to say find the inverse function, and by that I mean algebraically. You notice that I've already done part B there for you, which we'll go back and focus on that here in a moment, but here are some quick steps for being able to find the inverse function if I give you an original function f, right? So it says, given the function f, follow these steps to find the inverse f inverse, right? That's the way you would read that, not f -1. You would read that as f inverse, right? So it says to number 1, replace f of x with y. So in the function formula where you see f of x, it's just simpler notation to replace that with a single variable name like y. And then what we're going to actually do is we're going to interchange x and y. We're going to make x and y trade seats in the formula. So let's actually talk about how that is going to look like, right? So here in part A, we have f of x is equal to 2x minus 4. The first thing I'm going to do is I'm going to trade out that f of x for just a single variable name, maybe call it y. Y is equal to 2x minus 4, and then that's doing step 1. Step 2 says, of course, interchange x and y. So wherever there's a y, we're going to replace that with an x, and wherever there's an x, we're going to replace that with a y. Now, why would we do that? Well, because you'll notice here that in step 3, what it's now going to ask you to do, if I go ahead and fix my ink to shape there we go. Turn that off. You'll notice that now in step 3, it's going to say solve for y, okay? And the reason that you would want to do that after interchanging is because in order to get y by itself, you're going to have to do all the inverse operations. And if we're trying to find your inverse function, it had better have all the inverse operations of what we just started with. So that's why we interchange x and y, and then we solve for y here. And of course, applying inverse operations couldn't be simpler. I see a -4, so I'm just going to apply the inverse operation of that, which is +4. So that means on the left-hand side, I'm just going to be left with x plus 4 is equal to 2 times y. And then I need to finally divide everything by a 2. Okay, and I'm running out of room there, so I'm going to continue up here. So y by itself, it was on the right-hand side. I'm now rewriting it so that's on the left-hand side. That is going to be equal to x divided by 2. I can go ahead and rewrite that as 1/2 x, and then plus 4 over 2. I know that that simply is just going to simplify down to a simple 2. Okay, and then after that, once we have solved for y, which we've done here, it says rewrite y as f inverse of x. And so I'm going to replace the y with my inverse notation, f inverse of x, and that's going to be equal to 1/2 x plus 2, and there is my inverse function right there. So if you take a look at your inverse function and your original function, again, the idea is that these are machines that undo each other, right? If f turns an apple into a banana, then f inverse is going to take that banana and turn it back into the apple. It's going to undo what f did. You know, part B here for you, I invite you to go ahead and pause this if you go ahead and read through that on your own and just make some sense of that. And I'm just going to go ahead and move on. This very handy fact right here, it says two functions, f and f inverse, are truly going to be inverses of each other if, and only if, we can get these two things to check out here for us, right? So we are taking this back to our discussion of compositions of functions, which we talked about in a previous video, right? So if we were to go ahead and take f and throw something in, and then also take f inverse and throw something in, what we want to be able to say in these two statements is that f and f inverse truly do undo each other, okay? So, but in this first statement, what I want to say is that if you take your f machine and you throw inside of it f inverse of x, then because these guys undo each other, you're just going to see here that f is going to cancel out with f inverse, and you're just going to have simply x left over. Okay, so that first statement says that f machine undoes everything that f inverse machine does. And then in the second statement, we're just basically going to say the reverse of that, right? So if we were to take f inverse and throw in f of x, then of course, again, the idea being that f inverse is the machine that undoes what f does. again, going in the opposite direction, and this just simply leaves us with x here as well. So a way that you could show or verify that two functions are inverses of each other is by doing these compositions of functions like this and then showing that the result actually ends up being x, okay? It actually turns out to be a little bit involved because you do have to kind of algebraically show the two compositions, and it's been a while for that, so let me go ahead and show you an easier way, right? So it says here in example 3, verify the given functions f and g are inverses of each other. Looks like my note-taking program is taking its sweet time there. There we go. Those are the directions right there. So we were given this example here in part A. F of x is equal to 1/3 x minus 1, and then g of x is equal to 3x plus 3. We want to show that these are inverses of each other, okay? The easiest way to do this would be to start with one of your functions and find its inverse and see if that matches up to the other function you were given, right? So let's say that I just start off here with x. I'm going to follow that exact same process that we just discussed. I'm going to trade out f of x for y. So y is equal to 1/3 x minus 1. And then I'm just going to go ahead and interchange x and y. So everywhere there's a y, I'll put an x. Everywhere there's an x, I'll put a y. And then after that, I'm going to solve for y by applying all the inverse operations here. So I'm just going to simply add 1 to both sides. So on the left-hand side, x plus 1 is going to be equal to 1/3 y. And then, of course, to get rid of that 1/3 on the right-hand side, I just need to go through and multiply by 3. To everything, okay? So that means distribute 3 to every term of this equation, right? So we're going to end up here with 3x plus 3 is equal to y, which, of course, if I flip that around, it's going to give you y is equal to 3x plus 3. And now that we have y solved for, we could just go ahead and rewrite this as f inverse of x, of course, is going to be equal to 3x plus 3. The only thing that I would want to go ahead and do now, if I'm verifying that these two given functions are truly inverses of each other, is I just want to go ahead and take what I got here as my result, and I just want to simply go ahead and compare it to the g of x that I had in the initial problem. You could definitely see here that these guys have the exact same function formula. So what that's going to mean is that these truly are inverses of each other. So that's a little bit of an easier way to verify that two functions are inverses of each other than having to do the compositions of both functions and seeing that they both result in x. Okay, I've done the next example here for you. So again, make sure to go ahead and pause the screen here. And you can see the conclusion statement there. We're just basically stating that, yes, because they do match up, f and g are truly inverses of each other. And I want to go ahead and show you something that's pretty neat that you can use as a tool to check your answers by going ahead and doing this graphically, okay? So let's go ahead and go back to part A here where I had these two functions. I have f of x and I have g of x. These are two linear functions, so if you were to graph them, they would both be straight lines. And again, I want to show you something cool that happens with their graphs here. So here's a quick picture of that. I just did this very quickly in the TI-84. You'll notice that f of x has been done in blue, g of x has been done in red. And I want you to notice here that there is some mirroring symmetry going on, okay? If you draw this gray line in here, and that's the line y is equal to x in the coordinate plane, then you'll notice that there is perfect mirroring symmetry across this line, right? So for example, if you were to start off with the point over here, like maybe say the point 3, 0, if you were to mirror that across this line, then of course that would land right here, which would be a point with coordinates 0, 3. And so this follows suit with what we were saying before, is that if you have an original function f with a point x, y, we just want to go ahead and swap its coordinates to get the corresponding point on its inverse. And so graphically speaking, this is what that would look like. We have this mirroring action going on in the coordinate plane. And as it turns out, this will always happen with any set of inverse functions. And so I want you to find a blank space in your notes to go ahead and write this statement down, right? So this is a way that you can be checking your answers by graphing both and seeing that it does have that symmetry across the line y is equal to x, okay? So again, nothing to it but to just go ahead and plot both in the TI-84 and then plot the line y is equal to x. You can see that it has that mirroring symmetry, very, very easy to visually check, okay? In these next couple of examples, in example 4, it just says find the inverse of the following functions, and so let's just go ahead and do that. What you might notice here in part A is that we do have a domain restriction on our function, and we talked about these in the previous chapter 2 videos, right? So we're saying that this is your function formula. F is the machine that takes your input and squares it, but only for inputs that are greater than or equal to 0. So that's what this is. This is what, again, we call a domain restriction. We want to find the inverse of a function with a domain restriction. The good news for you is that nothing really changes here. We still would just go ahead and apply the exact same steps. So trade out f of x for y, and then make x and y trade spots. Just interchange them, and then solve for y here. And basically all that's going to amount to is, you guys know to undo an exponent of 2, we would want to go ahead and simply apply a plus or minus square root of both sides, okay? But here's the deal. If you apply a plus or minus square root, that means you're applying a negative square root, okay? And we want our inputs to always be positive here. And so that is something that kind of gives you the indicator or the green light to just go ahead and take a positive square root of both sides. All right, so this is going to give you y is equal to the square root of x, which of course means the inverse of f of x is equal to simply the square root of x. And we would want to go ahead and make sure that we tack on a domain restriction of our inverse function here, okay? And again, that's most simply done whenever you go ahead and take your function and you graph it, okay? So let me go ahead and show you the picture of this one real quick. So here is that over here. So in blue, you'll notice that I've got my f of x is equal to x squared with my domain restriction. And again, that domain restriction means that I'm only taking inputs that are either 0 itself or something that is greater than 0 on the x-axis. So a number like 1 or 2 or 3 or 4, etc., etc., going that way. That would be all the x's that are greater than or equal to 0, okay? When I plot my inverse that I just found, f inverse of x is equal to the square root of x, you'll notice that the x's that apply there, again, in order to get this mirroring action, are just going to be those x's that are going to start at 0, and basically same thing. Remember back in first semester when we talked about those magnets on the board and we dragged them up to the graph, right? So the domain restriction on this one would simply be all of the x's that are greater than or equal to 0. So it just happened to be the case that the domain restriction for both your original function and your inverse function turn out to be the same. But I would say that the easiest way to figure out what your domain restriction would be, if you have one, is to just simply graph both and then see what the domain would be from the graph. You notice that I've done part B here for you. That's something I would encourage you to pause the screen and try yourself. I'm going to go ahead and take care of part C here, which again, really nothing new here. We just are going to do the exact same process. Take f of x and trade it out for a y, and then make x and y trade seats, and then we're going to solve for that y here. Okay, and so subtract 5 from both sides. X minus 5 is going to be equal to 2y to the third. Divide both sides by 2. X minus 5, all divided by 2 is equal to y to the third. And then remember, to get rid of an exponent of 3, we would want to go ahead and apply a cube root of both sides. Okay, so on the left and on the right-hand side, a radical with an index of 3 is going to get rid of an exponent of 3 on the right-hand side. And so we'll go ahead and swap around the left and the right-hand sides here. I've got y solved for by itself. That is simply just going to be equal to the cube root of x minus 5, all divided by 2. And so that, of course, is going to mean that the inverse function f inverse of x is going to be simply the cube root of x minus 5 all divided by 2. Very, very simply done. And of course, you could whip out that TI-84 or other graphing utility like Desmos.com or GeoGebra or something like that. You can graph both along with the line y is equal to x, and you'd see that they do indeed have that mirroring symmetry like that. So again, if you haven't had a chance to write this this fun fact down, I definitely would encourage you to do that so that you can visually check that your answers are always correct when you find an inverse in this way. The only other thing that I want to talk about in this video is kind of talking about something that we talked about in the past, right? So when we first talked about functions, we talked about this visual way that you can verify if a graph is a graph of a function or not. We talked about the vertical line test. We said that if you were to take a vertical line, like maybe say if I were to go ahead and take my ruler here and make that vertical, maybe something like that, okay? If I picture that as a vertical line and then picture the edge of that ruler just kind of scanning through as I drag the ruler through, if there's any place where I can put this ruler so that the ruler's edge intersects the graph in more than one place, like maybe say right here, where I intersect in these two spots, like say right there and right here, then what that's going to mean, of course, is that this is not going to be a function. It does not pass the vertical line test, because that would be one x value that corresponds to more than one y value on the coordinate plane, okay? And that would be a problem for a function. Now, the idea here is that we need to go ahead and come up with a way to figure out if a given function has an inverse. And the way that you do that is by doing something very, very similar to the vertical line test. We're going to apply the horizontal line test, okay? And the idea is the exact same. If I were to take this ruler and flip it around so it becomes horizontal, it says the horizontal line test is used to determine whether or not the inverse of a relation is a function. The way you could think about this is, does the inverse exist or does it not? There are some functions out there where the inverse does not exist for a given function, and this is the way that you'll check to see if that's the case. And it says right here in bold, does it cross more than once? Then that means the inverse does not exist. The inverse is not a function. And so this would be an example of that, right? If I were to take my horizontal ruler here and again just kind of scan it through, you can see that this is an example of a problem where I could really put this ruler anywhere, and I can come up with examples where it would cross the graph more than once. Namely, right here, of course, where I'm crossing at these two places right here, and right there. That is a problem, and so what we would conclude is that we failed the horizontal line test in this problem, and we would conclude that the inverse does not exist. It's not a function, okay? And so let's take care of a couple of examples where we're taking a look at that, and then we'll call it a video here, right? So it says in example 5, the graph of the function f is given in these pictures, right? So it says determine whether the function is going to have an inverse, right? So determine whether the inverse is a function, in other words. So here in this first case, we have f of x is equal to 3x minus 1. This is a linear function. And again, I already have my ruler here. And again, you're just going to go ahead and take a look at the edge of the ruler. You could go ahead and very simply do this with like your pencil, just kind of holding it horizontally and scanning it through. But you notice that no matter where I take this ruler and put it on this graph, I can only ever get this ruler to cross the graph in one place. Like if I left the ruler right there, the only place that it's crossing the graph is right there. If I were to continue to scan this through, again, keeping this perfectly horizontal, the only place I'm crossing there is right there. I can never drag this ruler somewhere so that it's touching this graph in two places or more at once, okay? And so what that's going to mean is that this is going to be an example of a function that has an inverse, okay? So I'll say that f inverse is going to exist, and that's because it passes the horizontal line test, very simply, okay? In the case of the second graph, this is a quadratic, x squared plus 1. You'll notice that this is going to fail the horizontal line test, of course, because if I take this horizontal ruler here, there are a dozen places I could go ahead and land this thing so that it crosses in more than one space. So like, for example, say right here, where I cross the graph here, and I also cross right there, okay? And so this fails the horizontal line test. So what I might conclude down here is that f inverse does not exist. Another way to say that would be to say that f inverse is not a function, and that, of course, is because it fails the horizontal line test. It crossed the graph in two places when we scanned that horizontal ruler right through. And then this would be an absolute value function right here, the absolute value absolute value of x minus 3. And you can see here, very, very similar to the parabola, I can find a dozen places where I am crossing with a horizontal line more than once. So maybe say, namely, right here and right there. So this is going to be another example where f inverse does not exist. Again, another way to say that is that f inverse is not a function, and that, of course, again, is because it fails the horizontal line test. So if you cross more than once, then unfortunately you are not going to pass the horizontal line test, and the inverse function is not going to exist in that case. Okay, so that's all I have for this video. Thank you very much for your attention. If you guys have any questions, as always, feel free to let me know, and we can work together to get those results. But that's all I have for this one. Thank you very much for your attention, and I will speak to you guys in the next one.